Okay, so here we go. We have this formula, this equation. This equation is already balanced for you. Okay. What I would like to know, what we need to figure out is if I have 72 grams of C4H9OH. C4H9OH. I need to know how much energy will I be releasing. Okay, so first up, yes, we have to make it moles. Why do we have to make it moles? You guys remember from yesterday?
Because
Go ahead.
you can't, because grams isn't energy. Grams isn't.
No, grams is also because grams are mass. Mass can never be represented by a coefficient. So we're pulling on our past knowledge here. Mass can never be represented by a coefficient. So we have to do a mole conversion for something like this because we're doing a mole ratio. So first step is X mole of C4H9OH over 72 grams of C4H9OH. Because this is what's given. It's what is given. Okay, and what are we going to place this equal to?
You gotta find the molar mass.
We have to find the molar mass, so it's going to be 1 mole of C4H9OH. Each carbon is 12.01. So that's going to be 48.04 for the carbon. We have 10 hydrogens, so that's going to be 10.10.
48.04.
48.04 plus 10.1 plus 16.
74.14.
That's how many grams are in 1 mole of C4H9OH. So now,
Wait. I thought we put the molar mass on top.
no, because moles are on top here, moles has to be on top here. Grams are bottom here. Grams are here, grams are here. Molar mass is in grams, so it has to be. So grams has to go on the bottom. So we took the 4 hydrogen or the 4 carbons, which equals 48.04, plus 10 hydrogens, which equals 10.10, plus 1 oxygen, which is 16.00. Add those up, and that's how you get it.
72 divided by 1 times. Wait.
So we're going to do 72. It would be 72 times 1, then divided by the 74.
So it's 72 divided by 74.
Exactly.
Wait, where'd you get 74? 74.14.
That's the molar mass that we found. Like that's the 4 carbons, the 10 hydrogens, and the 1 oxygen. Added together. So this is now 72 is less than 74, so I should expect a 0. You said 97. We're in moles, so let's do the 7.1. He had said it's 0.971. Well, remember, I like to do 3 decimals for moles. So we'll use the 0.971. Probably not as much. I won't mind it because there's a range that I'll be looking for. Okay, we've got it in moles. Now, how do I find out how much energy will be released? So I'm doing. Hey, we're focusing on what we're doing right now. And when Aaron says we're going to do X kilojoules over the 0.971 mole of C4H9OH. What's going to go on top? What's that? I'm sorry, I can't understand what you just said. It is. The delta H is negative 2710 kilojoules over what? Over 1 mole of C4H9OH. Negative 2710, exactly. So what's our X going to be?
If you can toss me a calculator.
This number?
Negative 2,600.
So is
Oh,
X
is
gonna
that
be
gonna be-
Wait, I didn't know what this
Is
was
that-
like a
that's given.
two-step.
Wait, so is X gonna be
Negative
negative?
2,600.
It will be negative. X equals what?
Negative 2,631.41.
Does that make sense?
And then wait.
The amount of moles we had was less than 1, but it was close to it. The amount of energy that we're going to produce is less than the amount for a whole batch
This one,
because it was less than a full mole.
is this exothermic or endothermic?
What do you guys think?
Exo.
Why would you think it's exothermic?
Because it's negative.
Because it's negative. Okay.
Will all exos be negative?
Because it's
Yes.
a lower number. Yeah, because it's a lower number minus a higher number.
Well, I thought it was products minus reactants.
It is.
Exactly, yeah.
Oh, wait. So exos will always be negative, KJ?
Yeah.
Okay, so now what we're going to do is we're going to make our potential energy diagram. We're still going to use this equation. We're still going to use this delta H. We're not going to use this problem. This problem has nothing to do with this. So what we're going to do is I'm going to fold this like this. And that's what we're going to use. Okay? So how do we make our potential energy diagram using this information? Okay, let's start it off. What is our scale going to be?
270 negative 270.
No, our scale. How high are we going to go?
Oh my god. 293,100.
What's that?
3,100.
3,150 is going to be our highest point. So what do you guys want to put the?
Whoa.
4,000 is a little high.
3,120.
Why don't we do like 3,250?
That's like
How do we know that? 31
It's a nice round number though. It's like 1/4 of the way to 4,000
from 3,000.
from 3,000. Yes,
How do we know that 3,100 is
because we're saying that the activated complex is at 3,150.
3,150?
Okay, so we know in the center of this graph, around 3,150 is where our activated complex is going to be. Where's our reactance going to be? So 2,950 is going to be somewhere around here, right? Okay. Now we have to figure out the rest. Where's our products going to be?
2,950 minus 2,631. Or minus
Plus
2,710.
2710, right?
Yeah, minus.
Plus.
No,
I
minus.
thought it was products minus reactants.
Well, what that would be is negative minus a minus. It's weird. This is delta H. The delta H is negative. So what that's telling me is my products will be 2710 less than the reactants. Does that make sense to you? Because the difference is I'm losing 2710.
It's 240.
So around 240 will be our products.
Wait, only 240?
Yeah,
Yep.
but where did you get 240?
You do 2.
The 2950 minus this 2710 because our reactants will be 2710 higher than the products.
Wouldn't it be plus? Oh no.
To get to the 2710 being negative, it would be 240 minus the 2950. Does that make sense?
If the delta H was positive, would it then be 2,950 plus 2,000?
Yep. All right, so now we got to connect this. All right. So first thing here, what is this measurement that says it's 2950 going to be called? We'll label this A. What A is the what? Potential energy of the reactants. Okay. What about letter B? Letter B is measuring from the reactants to the activated complex. This is our activation energy. Or E sub A. All right. Yes. What about the center measurement right here? What about the activated complex? There's the potential energy of the activated complex.
E is equal to 200, right? Yes? No?
I don't know what you just said. Something about 200.
B is equal to 200.
I haven't done an E.
B. B as in Ben.
It's 3250 minus 2.
It's 3150 minus the 2950.
Perfect. That's all I need to know.
Yes.
Are we gonna have to like pick these out from a word bank, or do we? Are we gonna have to like write?
It's probably not gonna.
Oh, word bank.
Yeah, can we have a word bank? That's actually
Well,
great.
that's what I'm asking.
There's not gonna be a word bank.
So you just have to
You
write
need to
something.
know these
Oh,
things.
what?
Bro, that's
That's why I'm trying to tell you.
Are we
Anything
gonna
that
have to fill this in?
anything that comes from the bottom of the graph is always going to be potential energy of that point of the line. So this is the potential energy of the reactants because that's the reactant point of the line. This is the potential energy of the activated complex because that's the point on the line.
Are
Okay?
we gonna have to draw the graph too?
I'm not sure what it has on it.
Can you like think about it?
No.
That's why.
Guys, I did not write the test. The test was written by the science curriculum team for everybody to do it so that we can gather data on whether or not everybody's getting the same education. Okay? I don't have any control over the test at all. When they put it on the Mastery Manager or when they print it, they tell me. I don't have any control to change anything. So, what is this point up here called?
Activated complex.
D is the activated complex.
Oh.
Okay. What is the difference between the reactants and the products called?
The reactants of the products?
Reverse reaction.
Nope, that's not right.
This one is the delta H of the reaction, which is equal to the heat.
Or change in heat.
Not change in heat, it's the heat of
change.
the reaction. Everybody cool with this so far?
E is equal to
Delta
H.
Yep.
Delta.
You notice I'm changing all the letters around from the way we've done it before. That's because I don't want you guys to think that the letter is what is the label
we
of
don't
it.
have the dotted line.
Well, not yet. We could have it though.
Please don't.
The delta H.
You don't like a dotted
H
line?
is equal to
What was it
heat
gonna be
of
on the
reaction.
test?
Yeah. What is F going to be?
The potential energy of the product.
Let me get the next one.
What's F?
PE of products.
That's it. We're done.
Nope.
What's B? Oh,
What would G be?
Where's G? G is the active. No,
Potential
hold on.
energy
No,
of
it's not.
complex.
It's not the potential energy. It's the activation energy of the
Reverse
possible
reaction.
reverse reaction.
That's a lot of words.
Of the potential reverse reaction. I don't know which word
He
you
said
like.
that you could say either.
I know, but he likes one more.
Mr. Cole, we can't see your paper anymore.
Potential reverse reaction.
Wait for that.
Italy.
Why are you talking to Italy when you're in class?
She said hot.
Italy. That's her name.
Italy?
That's a
like the place?
That's a really cool name.
What's wrong with the name?
Why y'all messing with my girl?
I'm so fascinated with the name Italy.
Why they messing with my girl?
That's a really
You
cool
know Italy.
I know she my girl.
That's a really
Well, I just never heard that before.
She's
You
super
never heard of a
awesome.
person named Italy?
Hold on, wait. Time out. Time out here, guys. Everybody's thinking we're making fun of her name. We're not. Just think it's really cool.
Okay. If we were to draw a catalyzed reaction, tell me some of the things that it must have. If I were drawing a catalyzed reaction, what must it have? Dotted line is what we do. Tell me some things about that dotted line. What are things that I need to know about the dotted line? Go ahead, Aaron.
The activated complex would be lower.
The activated complex will be lower because it lowers the activation energy.
Yeah.
What else must I know?
You must know that it takes a shorter path. The delta H, no. Yeah, no.
It's not a
reverse reaction
shorter
is less.
path as
Shortcut, that's how I think of it too.
well, what is it reducing? It's reducing what the activation energy. So it's not really making.
The hump will be smaller.
The hump is lower.
Okay, know what I call it.
But why does it have a hump? Why does it still have to rise above the reactants?
It has to have some, like it has to have activation energy.
It has to have some energy to break all the bonds
Right.
because breaking bonds requires energy. And then what about when it drops down?
It drops down fast.
Does a catalyst change the reactants or the products at all? Why does it not?
Reaction, the middle part.
Why doesn't it change the reaction?
No, it
Yes.
does change it.
It does it.
The same like stuff to make that reaction.
Guys, here's the deal. A catalyst when put into a reaction will reduce the activation energy, which allows for it to go faster.
He's asleep. This was important.
See, now he's gonna play with it.
So since it goes faster because it has lower reactivation energy, it still requires energy to break the bonds, and it will still release energy when it's forming bonds.
So the delta H will still be the same.
The delta H will still remain the same. The reason why it does this is the catalyst does not take part in the reaction. It's just an impetus for it to go faster. That's all it is. All right.
Write down the facts on
We have
paper.
2 minutes. 1 minute left.
Can I leave my cousin